Here we are in the last section of chapter 4, which is an extremely important section. It is modeling with exponential functions. Now, exponential functions are honestly more important for application problems than the linear ones we were working with in chapters 2 and 3. They're critical to understanding things like compound interest, population growth, the level of medication in your bloodstream, radioactive decay, and much, much, much more. So let's remind ourselves of just one little thing. Back here in section 4.4, we talked about how, over here on the right, if A is greater than 0 and B is greater than 1, we have exponential growth. So things like compound interest would work this way. Population growth works this way, and so on. And then if A is greater than 0, but B is a fraction between 0 and 1, or a decimal between 0 and 1, then you have exponential decay. Your values are going down, such as radioactive decay. All right, so keep that in mind because it's going to become very important to us in this section. Down here. Okay, so let's read this problem. We have a $10,000 deposit made into an account that pays 4% interest compounded annually. Let M of t represent the amount of money in the account after t years. Fill in the value of fill in the table of values for the amount of money in the account. Use this to find the model for M of t by hand. Okay, so we need to figure out some values here. Let's start off with the beginning amount. So at time 0, how much money are we going to have in this account? Well, that'd be $10,000, right? Because we're depositing $10,000 into the account. But the account pays 4% interest. Now, what that means is that on the first year, you get 4% of the $10,000. And the next year, you're going to get 4% of that $10,000 plus whatever interest you had before. So it'll keep growing larger and larger and larger. It's not going to be a set amount. 4% interest doesn't mean that, every year you get $40 more. That's not how it works. It's saying every year you get 4% more, right? So you have to take 4% of how much money is sitting in the account. Okay, so we're going to need to fill out another values. So let's think here. I had 10,000 to begin with. So after 1 year, I'm going to have 4% more from that 10,000. Now, what a lot of students say to me is they'll say, okay, let's take 10,000, and times it by 0.04, which is a great idea in theory, but that means you've got $400. And we didn't all of a sudden take the account and change it to $400. So multiplying by 0.04 is the right thought, but we need a little bit more than that. Now, remember, we said that the amount in your account is going to grow based off of your base, right? So since our base is a number bigger than 1 is how it's going to be. If our base is greater than 1, that's how it's going to grow, right? So we need a number that's bigger than 1, and 0.04 is not bigger than 1. But what we could do is we could say 1.04. So if we multiply 10,000, there it is, times 1.04. All right, this is bigger than 1. Let's press enter and see. It gets us the 400 in interest that we're looking for, but it also gets us 10,000 back, because what essentially you're doing is taking 1 times 10,000, there's your $10,000 back, plus 4% of 10,000, there's your $400 in interest. So you have your original amount of 10,000 plus your 400 in interest. Now the next year, you're going to do it again. So you're going to take 10,400 and you're going to multiply that times 1.04. Because you want the 10,400 back, that's why you multiply by 1, but then you want 4% interest on all of that. And that gets you 10,816. And then we might as well do it one more time for the last year, 1.04. So the 1 will get me the 10,816 back, and the 0.04 will get me the 4% interest on all of that. Okay, so there are my numbers right there. So it was 10,400. And then 10,816, and then 11248.64. You can see it's growing and growing. So the first year was $400 in interest, the next year it was $416 in interest, and the next year, oh, who knows how much that is, but we can find it. If we take that last answer and we subtract 10,816, we can find we got $432 in interest. So every year we're getting more and more and more interest. This is how bank accounts work, right? This is how all savings accounts work. It's also how retirement accounts work. So if you have any desire to retire at some point, it would be helpful to know how this works. This is what compound interest does for you. All right, so let me type up what we did over here. One sec. There we go. So we were multiplying by 1.04 to work our way down the table. And then we can figure out from there what our equation is going to be. It's m of t is equal to, now we need a times b to the t, right? Now a, remember, is our y-intercept, which if we look at our table, it's rather obvious that it's 10,000, right? It was our starting amount. Okay, so I'm going to have 10,000. And then b is our multiplier, our constant multiplier, which in our case is 1.04. Again, it has to be bigger than 1, otherwise it's not going to grow. You've got to have a number bigger than 1. The 1 here gets you your 10,000 back. The 0.04 gets you your interest. That's how all compound interest works. Well, simple compound interest. All right, so we're done with that problem. Is that part of it? So now we need to answer the questions. What was A in our model and what does it mean? Well, A was 10,000. Now what does it represent? The starting amount, right? So at time 0 we have $10,000. So the starting deposit in the account was $10,000. All right, now what was the base B? That's the 1.04. 1.04. What does it represent? Well, that's a little tricky. So let's start with B is here. B is 1.04, which hopefully you all understand is 104%. Okay? So if we take 104% and we take away 100%, we're going to have the 4% interest. And that's what really matters to us, is the interest, right? The 100, remember, the 1 was really just to get you back the amount that you had to begin with. So in other words, it's making it so that it grows. That's why you need the 1. But the actual amount that you're growing by is the 4% extra that you've got on there. If you had just 1, like let's say the base was just 1, then you would never grow, right? That's the equivalent of putting the money in your mattress. It just stays 10,000, 10,000, 10,000 forever. Right? It's the extra little bit that the bank gives you is the reason that you want to go to a bank in the first place to deposit it, right? So that 4%, that's what makes it great to deposit into a bank. Okay, so although I personally would prefer a credit union. We can talk about that in econ class. All right, so we have 4%. So every year, the amount of money in the account increases by 4%. Okay. How much money will be in the account after 15 years? Well, we're just going to take 15 and plug it into our lovely equation here. So we're going to find M of 15. M of 15, which is 10,000 times 1.04 to the 15. And we have calculators to figure this stuff out. Let's see here. Clear. 10,000 times 1.04 to the 15. 18,009.435. Let's round to 44. This is money, right? So it makes sense to make it a singular amount like that. All right, so there we go. And then I'm going to put that in a box. Okay, so if you let the money sit in the account for 15 years, it'll grow to $18,000 from $10,000. Not bad. Of course, you'd like a little bit higher interest, right, than that, generally. Okay, so we've learned some valuable lessons here. In an exponential model, f of x equals a times b to the x. A represents your starting value, how much you have at time 0. B represents the percent of change. So you convert the value B to a percent and then you subtract 100. Maybe I'm going to highlight that. Convert it to a percent and subtract from 100 or subtract 100, right? Why is it 100? Well, because it's always 1, right? You need B to be greater than 1 or B to be less than 1. If it was 1 flat, it wouldn't go anywhere, right? So we're always considered between the difference between it and 1, which is 100%. This gives the percent rate of change. Let's see, for half-life, that's the time, another couple definitions. The half-life is the time required for something to fall to half of its starting value. Particularly useful in radioactive decay, but also drug dosages. So for nursing and allied health biology class, how long does it take for a certain drug to work its way through the system? Doubling time is the time it takes for something to grow to double its value. Again, that's really useful for biology. How long does it take, the number of fruit flies to double, the number of bacteria to double, that kind of thing. Very useful stuff. And computer science as well. How long does this take for, this process to double, etc. All right, I want to stop right there, even though we have minutes left, because I don't want to get stuck in the middle of this half-life problem. So I'll see you back here for this drug half-life problem.